Right, you all. Barely Berry Jr. back with some more classical dynamics. Earlier, we found the equation for a particle that has moved a certain distance xo in a more roundabout but more straightforward method than the textbook did. But we do end up with the exact same equation, and we'll continue with some more things in a text. So you're doing this result. We have Vt at a certain time. I guess we can call this V naught equals V at a certain time to get us the velocity at x naught, V at x naught, and it's 2g x naught sine theta, same thing the book has, all right? So we know we can go a roundabout way to get that. If the coefficient of static friction, so let's do example 2.2. It's the coefficient of static friction between the block and the plane. In the previous example is mu s equals 0.4. So now we're going back to the block here with the full equation, including friction. At what angle theta will the block start sliding if it is initially at rest? So we have our sketch. We need a new sketch to indicate the additional force of friction. I already have that there. The static frictional force, and you notice they call it static, so friction is considered an electrostatic force as the approximate minimum value. So we'll call this F. So F equals mu naught S times the normal force, and that's F max. So the max friction force is the coefficient of friction times the normal force. F max friction max is the coefficient of friction times the normal force. And this becomes the component in the y direction. We have F net equals Fg plus N plus F. We have the force of gravity pulling down, the normal force pushing up, and the friction force pushing opposite the direction of motion. So that's going to be Fgx minus Fi plus Fgy plus Nj, and Fgy equals N. So that makes this part equal 0. So we have Ma equals Fgx minus F. And FGX is FG sine theta. So that equals FG sine theta minus F, which is going in the opposite direction. So MX double dot equals FG sine theta minus the normal force is the same thing as FG cosine theta times the coefficient of friction. So we can say mx double dot equals FG sine theta minus the coefficient of friction cosine theta. And this is all in the x direction. The static frictional force Fs will be some value Fx is less than Fmax, required to keep x dot dot equals 0. So what they're saying is we want what angle, what theta, block starts moving. So Fs will be less than or equal to F max. It can't be more than F max. Such that x dot dot equals 0. And we can actually call this G and x dot dot, because that'll be mg. And the m's will cancel as they normally do. System. It's interesting that the mass still cancels even though we have friction. Does this mean that friction is the same regardless of mass? It seems like friction to be different depending on the mass. But we'll keep going. Oh, the mass is greater to cause friction to be heavier, but also the mass is greater to help it slide past friction. So I guess so suppose balances out. The static frictional force Fs will be some value less than or equal to F max, such that the acceleration is 0. That is to keep the block at rest. However, as the angle theta of the plane increases, eventually the static friction force will be unable to keep the block at rest. At that angle theta prime, Fs becomes max frictional force. So apparently, if the block is horizontal, F is the coefficient of friction times the normal force. Technically, there would be no friction force because the block is not going downward to the left at all, it's just stopped. So the friction force is Fg sine theta. The theta here is 0. Fg cosine theta is the friction force. 1. So the normal force is just Fg. So the bigger the angle, the lower will the force be that's holding it to the block. If the block is vertical, then theta will be 90 degrees and cosine will be 0. So it'll be 0 normal force because it's not pushed into the block at all. So the maximum normal force is when the block is flat. So the normal force, the maximum potential normal force will decrease as the block is tilted higher and higher until eventually, at this point, theta will be 90 degrees. Cosine of 90 is 0. Therefore, the object will be in free fall. So sine of 90 is 1. And there will be no normal force and thus no friction force. So the maximum friction force is when the block is flat. When the block is tilted, it's somewhere in the middle, but steadily getting less. But we know that the friction force required to keep the block static. So basically we have x dot dot equals g sine theta minus mu cosine theta. And they have this as equation 2.15. Just before the block starts to slide, acceleration is 0. So 0 equals g sine theta minus mu cosine theta. So I can divide both sides by g. Say 0 equals sine theta minus mu cosine theta. So I can say sine theta equals mu cosine theta. Tan theta equals mu equals 0.4. So theta equals tan inverse 0.4 angle static. The block is not moving because acceleration is 0 and it never was released. So that equals 21 degrees. So at this angle, acceleration is 0, which means that at this angle, the downward force due to gravity balances the upward force due to the friction. So since those forces balance, there's no movement, and that angle is at 21.8 degrees. If theta is greater than 21.8 degrees, it starts to slide. If theta is less than or equal to 21.8 degrees, then it stays where it is. So that's good to know. After the block in the previous example begins to slide, the coefficient of kinetic sliding friction becomes 0.3. Find the acceleration for the angle 30 degrees. We've already calculated in the x direction, x dot dot equals g sine theta minus mu cosine theta. So they're saying, and that's g sine 30, theta equals 30, mu equals 0.3, sine 30 minus mu cosine 30 minus 0.3 cosine 30, all right? And this is equals 9.8 meters over second squared. Got that? So using our unit circle, sine of 30 is 1/2, cosine of 30 is square root of 3 over 2. 1/2 minus 0.9 over 2, nope, 0.3 square root of 3 over 2. So that's going to equal 0.5 minus 0.3 square root of 3 over 2. My calculator. So that's 9.8 meters per second squared times 0.24. So the acceleration is going to be 2.35 meters per second squared. So at 30 degrees with the coefficient of friction of 0.3, it'll move at 2.35 meters per second squared. G sine theta, mu cosine theta. They definitely have typos in this book. If you look here, it's saying the acceleration is 0.24 grams. Acceleration is not in grams. Acceleration is meters per second squared. So I have no idea what these people did or what they're doing. Generally, the force of static friction is greater than that of kinetic friction. This can be observed in a simple experiment. If we lower the angle theta below 16.7, we find that acceleration is less than 0. And the block eventually stops. If we raise the block back up above theta 16.7, we find that the block does not start sliding again until theta is greater than 22 degrees. saying static friction is greater than kinetic friction. It's harder to get something moving than it is to stop something moving. This can be observed by a simple experiment. If we lower the angle below 16.7 degrees, we find that acceleration is less than zero. We start the block moving and the block eventually stops. If we raise the block back above 16.7, we find the block does not start moving again until theta is greater than 22 degrees. i.e., the static friction determines when it starts moving again. There is not a discontinuous acceleration as the block starts moving because of the difference between mu(s) and mu(k). For small speeds, the coefficient of friction changes rather quickly from mu(s) to mu(k). The subject of friction is still an interesting and important area of research. There are still surprises. For example, even though we calculate the absolute value of the frictional force, F as mu n, research has shown that the frictional force is directly proportional to, not to the load, but to the microscopic area of contact between two objects, as opposed to the apparent contact area. So this sort of answers my question earlier about the amount of mass as a determinant. What it's saying is not directly proportional to the load. So it's not directly proportional to how much mass is there, but the contact size. We use mu n as an approximation because as n increases, so does the actual contact area on a microscopic level. So more mass causes more friction because there's more contact points. For hundreds of years before the 1940s, they accepted that the load, the mass, and not the area was directly responsible. We also believe that the static friction force is larger than the kinetic friction force because the bonding of atoms between the two objects does not have as much time to develop in kinetic motion. Okay, so that's that section. The effects of retarding forces. This is still in section 2.4. Wow, I'm already halfway through chapter 2. So this is a long section, though. I'm on 58 right now. So this section is a long section. So the previous sections were pretty short. The effects of retarding forces. We should emphasize that the force F in equation 2.7 is not necessarily constant. And indeed, it may consist of several distinct parts as seen in the previous examples. For example, if a particle falls in a constant gravitational field, the gravitational force is Fg equals mg, where g is the acceleration of gravity. And if in addition a retarding force Fr exists, that is some function of the instantaneous speed, then the total force is F equals Fg plus Fr. So this is F net, which equals mg plus FRV. It is frequently sufficient to consider that FRV is simply proportional to some power of the speed. In general, real retarding forces are more complicated, but the power law approximation is useful in many instances in which the speed does not vary greatly. Even more to the point, if Fr is proportional to the velocity of some power, so Fr is proportional to some power on the velocity, then the equation of motion can usually be integrated directly, whereas if the true velocity dependence were used, numerical integration would probably be necessary. With the power law approximation, we can then write equals mg plus mkv with its power, and the direction is given by this. We have the velocity v divided by the magnitude of v, so that gives us a direction. So now we say mg equals mkv and v hat for the direction of the velocity, where k is a positive constant that specifies the strength of the retarding force, and where v over v is a unit vector in the direction of v, which we figured out. Experimentally, we find that for a relatively small object moving in air, n is about 1 for velocities less than about 24 meters per second. For velocities higher than that, but below the speed of sound, the retarding force is approximately proportional to the square of velocity. So we have Fr equals, or is proportional to, Vn, n equals 1 if v is less than 24 meters per second, n equals 2 for v is less than or equal to 330 meters per second. For simplicity, the v squared dependence is usually taken for speeds up to the speed of sound. The effect of air resistance is important for a ping pong ball smashed to an opponent, high-flying softball hit deep to the outfield, a golfer's chip shot, and a mortar shell lofted against an enemy. Extensive tabulations have been made for military ballistics of projectiles of various sorts, for the velocity as a function of flight time. There are several forces on an actual projectile in flight. The air resistance force is called the drag, W, and is opposite to the projectile's velocity as shown in figure 2.3a. The velocity v is normally not along the symmetric axis of the shell. The component of force acting perpendicular to the drag is called lift. There may also be various other forces due to the projectile's spin and oscillation, and the calculation of a projectile's ballistic trajectory is quite complex. The Prandtl expression for the air resistance is, so this is Prandtl expression, VTL. W equals 1/2 CW. Rho for density, A V squared. And that's equation 2.21, where CW is the dimensionless drag coefficient, Rho is the air density. So CW, drag coefficient. Rho equals air density. V equals velocity. We know this is squared, so that suggests greater than 24 meters per second, but less than 330 meters per second. A is area of object, cross section. Is perpendicular to the velocity. Figure 2.3b, we plot some typical values for CW, and in figure 2.3c and d, we display the calculated air resistance. W, using equation 2.21 for a projectile diameter of 10 centimeters, and using the values of CW shown. The air resistance increases dramatically near the speed of sound. Below speeds of about 400 meters per second, it is evident that an equation of at least second degree is necessary to describe the resistive force. For higher speeds, the retarding force varies approximately linearly with speed. So we have our object. This is our projectile. So we have velocity going certainly directly in line with the object. This is the central line of the object. So this angle theta, I'll just call it alpha, it's the angle R from the center line that the velocity is. Drag W equals drag. We have FG going straight down. And we have at a right angle and what is L again? Lift. This is velocity. Lift is perpendicular to drag, which is also perpendicular to velocity. I guess something shot straight up has zero lift. Right? Drag coefficient really jumps up at Mach 1. Air resistance. The bottom one is velocity versus air resistance force. So we see the air resistance force definitely increases with speed. (2.3a) Aerodynamic forces acting on a projectile. W is the drag, air resistive force, and it's opposite the velocity of the projectile. V. Notice that V may be at an angle alpha from the symmetry axis of the projectile. The component of force acting perpendicular to the drag is called lift. The point D is the center of pressure. This is D. Finally, gravitational force acts down if the center of pressure is not at a projectile center of mass. There's also a torque about the center of mass. The drag coefficient CW from the Rhind metal resistance law is plotted versus the Mach number m. Notice the large change near the speed of sound where m equals 1. The resistive force drag is shown as a function of the velocity for a projectile diameter of 10 centimeters. Notice the inflection near the speed of sound. Right here. Same as C for higher velocities. Notice there's no inflection because it's already greater than the speed of sound. D equals center of pressure. Several examples of motion of particles subjected to various forces are given below. These examples are particularly good to begin computer calculations using any of the available commercial math programs or spreadsheets, or for the student to write their own programs. The computer results, especially the plots, can often be compared with the analytical results presented here. Some of the figures shown in this section were produced using a computer, and several end-of-chapter problems are meant to develop the student computer experience if so desired by the instructor or the student. All right? We'll take a break here. It's been almost 40 minutes, a good time for a break, and we'll come back and continue from here with these examples.